Hello everyone, welcome to our fifth lecture in the Natural Language Processing and Information Retrieval course. And in this lecture we will start to cover an interesting topic, which is language modeling. What is language modeling exactly? It's basically trying to generate the next token in a sentence, or what we can call more formally the assigning of probabilities to sentences. So how probable a certain sentence is, well, we will formulate that later as what is the probability of having a token after a sequence of words. How will this task be useful? It is useful for machine translation. So for example, the probability of high winds tonight should in essence be larger than the probability of large winds tonight, based on the probability that the word high will always be followed by wind as opposed to large, which is less likely to be followed by wind. It can also be used for spelling correction, something that is implemented some way or another using your autocorrect keyboards. So the probability of about 15 minutes from should be larger than the probability of about 15 minutes from. So this will be higher than this, and therefore this sentence will be more likely to be generated than this sentence. It is also useful in speech recognition. So whenever you are hearing utterances, you will probably assign an utterance to I saw a van, as opposed to an utterance that would be transcribed as eyes awe of an. It's also used for text summarization, for question answering, because this is essentially one part of what you will be doing in the project, which is chatbots. So in question answering, whenever you are given a question, the most probable answer would be something based on how you can compute the probability of a sentence. So what is the goal? And we need to formulate it now as something that we can compute. So what we will cover in this lecture is probabilistic language models. Hopefully we will have a lecture in which we cover deep neural network models, and through these we can see that language models can themselves be produced using deep neural networks. So let's focus on the more straightforward formulation of this problem, which will make us understand how it is solved. The goal would be to compute the probability of a sentence. And the probability of a sentence is in essence the collection or the aggregation of the probabilities of the words in that sentence. But it is not as simple as that. Each word here is dependent upon the appearance of the previous word. So here you have what we call a sequence. That means there is some probability here that will be higher after certain words, and there is a probability here that will be higher after a certain set of words. It is not independent. So how can we make this task a little bit easier? You can just formulate it as the probability of an upcoming word given the previous words, which will make things a little bit simpler for us to compute. So it is the probability of word n given the probabilities of all of the words preceding n. So this is the conditional probability then. How can you compute these probabilities? Then you reduce the probability of a whole sentence as the probability of the nth word given all of the probabilities of the words preceding that nth word. And we will see how we can simplify this. But this is in essence what a language model is. Usually, you would assume that it should be the grammar, but the language model is the standard term that was given or coined this case of assigning a probability to a sentence. So how do we proceed to compute this probability? In essence, it's a joint probability. if you want to compute the probability of the sentence, its water is so transparent that it's basically the joint probability of all of these words combined in this order. But this will prove challenging to compute, so we'll try to simplify it. How can we simplify it? We can use the chain rule of probability. What is the chain rule of probability? Basically, you need to use the conditional probability in a cascaded fashion, starting with the first word. So essentially, it is this. It's the probability of the first word, then multiplied by the probability of the second word. However, this is conditioned on the first word. Then you multiply by the probability of the third word. However, it is conditioned on the previous two words. Then it's the probability of the next word conditioned on the probabilities of all of the other words before it. And as you recall, the conditional probability is basically the joint probability divided by the given. So this is how you can actually compute it. It's the probability of the given and then multiplied by the conditional probabilities of all the others that should depend on that given. So this is basically a generalization of the conditional probability. Instead of having only two events or two variables to compute for, you have multiple ones, and then you need to cascade the conditional probability on the multiple ones. So the generalization of the chain rule is that whenever you have a set of words, you just compute the probability of the first, and then you compute cascading conditional probabilities of each word in the sequence, each following word in the sequence, given the probabilities of the previous words. So basically, if you have a sentence such as this one, the German University in Cairo, it's basically the probability of the multiplied by the probability of German given the multiplied by the probability of university given the German, and so on. So here we can use the projection symbol in mathematics to formulate this into a more generic formula, which is the probability of a word I given all of the probabilities of the preceding words to I. How we can do these computations then? We need to provide estimates of these probabilities. So basically what you have to do is, in order to compute this conditional probability, you basically have to count the number of times in which the entire sentence appears and divide it by the number of times in which the precedent appears. This is the precedent. Okay, let's clear this and let's use another color here. So this is the precedence. And this is the entire sentence in which Cairo appears immediately after the sentence. So basically, in order to compute this probability, what you need to do is you need to count the occurrences of the sentence in a text, in a corpus, and then divide it by the number of times this precedent itself happens. I'm sure that you can guess that the probability of Cairo given the German University N is going to be very high, because almost always whenever you have the German University N, it's going to be followed by Cairo, and you will not find the German University N in any other context. So this probability will almost always be equal to 1. So the problem here is that whenever you try to compute this count here, especially if the sentences are long enough, you will never be able to see enough data in order to estimate these counts properly and appropriately. So maybe in corpora related to all of the documents in the German University in Cairo, you will find this sentence and this sentence quite often. But we are talking about general sentences. So you will not probably find a corpus in which a complete sentence repeats itself over and over again. You can find a word repeating a lot. You can even find a phrase combining two words repeating a lot. But the longer the sentence, the less likely it is that the entire sentence will appear many times, or enough times to enable us to compute these counts. So the problem is we need to approximate this probability. We need to approximate these counts. How can we do this? We can use the Markov assumption in that case. What did Andrei Markov say as an assumption that will allow us to compute the probability of a very long sentence? He essentially said this: the probability of a word giving a long number of words before it in a sequence can be roughly equal to the probability of that word given the last word in the sequence. So instead of having to go and count all of these words combined in a sentence in a corpus, you just can go and count this word in a corpus and then see how many times does Cairo appear after it. And you will essentially have something close to the probability that you could have computed from the entire sentence as a whole. Maybe you can make things a little bit better by not using the unigram and maybe using the bigram. And maybe you can make things a little bit even better by using the trigram. But you will see that beyond that, the number of occurrences of a sentence in a text will be very low, so that denominator here is going to be very low as well. So the Markov assumption then will boil down to, instead of having to compute all of the words, the probability of a word given all of the words preceding that word, you just use a window of length k. Now this k could be 0, indicating that you are just computing the probability of the word with no prior information included. And you can either use 1 in order to compute the conditional probability based on a unigram, or you can use k equal to 2 to compute the conditional probability of a word based on a bigram, and so on. So basically this will allow us to make more manageable computations that will probably bring us closer to computing this joint probability, which proves to be very elusive and difficult to compute from corpuses. What if you use k equal to 0? You end up with a unigram model in which you are using only the word to compute the probabilities, the probability of the sentence. So you basically compute each word's probability in isolation, and then you multiply all of them, which makes the words independent. This is not the best approach, but it's one of the approaches that you can actually use, and it will prove to be useful later in the discussion of how to better improve the accuracy. So basically, if you want to compute the probability of the sentence German University in Cairo, you just compute the probability of German, multiply it by the probability of university, then multiply it by the probability of N, and then multiply it by the probability of Cairo. Basic independent distribution of the words. Now, how do you compute the probability of each one? You just count the number of times each word appears over the corpus size. Very basic. Why do we divide by the corpus size? Because we don't have a prior. The prior is 0. A slightly better model is to use the bigram model. So you compute the conditional probability of a word based only on the preceding word. Here, k is equal to 1. So that means you have only one word preceding that you can actually use. So that means the probability of German University in Cairo is going to be roughly, and let's not forget that this is an approximation. It's not the exact probability. It's the probability of German giving nothing. Here it's the start of a sentence. And then you have the probability of university given German, probability of N given university, probability of Cairo given N, and then probability of end of sentence given Cairo. I think you can just get the gist of how n-grams can be built out of this unigram or bigram. So you can extend to trigrams, you can extend to 4 grams, 5 grams, n-grams, you can extend to however long you want. Basically, the counting is the same and the division to compute the probability is going to be the same. However, we did indicate that using longer sentences would be great because it will provide us with more meaningful representations of the sentence. However, it is difficult because you don't have so many counts related to the sentence. So you can be tempted to use the 5 grams, the 6 grams, and longer, but the problem is you will not find so many counts of the sentence in using 5 grams or 6 grams or whatever in the text. However, the problem is using shorter grams, bigrams, trigrams, 4 grams, that's definitely shorter than a typical sentence length. The problem is when you use less grams, you don't have a sufficient understanding and information related to the word that you are trying to generate for the sentence. Because the language usually has long dependencies or long distance dependencies. Let's take this very nice example to showcase what it means to have a long term or long distance dependency. You have a sentence here that says, the computer which I had just put into the machine room on the 5th floor crashed. So let's assume that you are trying to generate the word crashed. If you use a unigram model, you just compute the probability of crashed and each of the word's probabilities independently and then multiply, and then you see if the word crash will have a high probability of being generated after the sentence. If you want to use a bigram, then you are inspecting the probability of the word crashed after the word floor. Now, I guess you can see that the count of floor crashed will be very low compared to the count of floor. Why is that? Because crashed does not usually follow the word floor. And even if you try to extend to trigrams, 4 grams, 5 grams, or whatever, you will still end up with a very low probability of these counts, because crashed is a word that does not usually get associated with all of these words. However, the word crashed is usually associated with the word computer. Very strong association here. However, by the time you get to this window, you will have a very low count of this entire sentence, starting with computer and ending with crashed. That's why even if you increase the n-grams, you will not end with a high probability associating computer and crashed, which is usually what you will find in the text, as opposed to the probability of the entire sentence that you have here without the word crashed. However, in most of the cases, the n-grams will actually work fine with us. Again, remember that we are trying to find an approximation and it's all built on probabilities. Here is an illustration of how you do compute the probabilities. We did highlight how this works already. So this is what we basically call the maximum likelihood estimate. Why is it called the maximum likelihood estimate? Because you are basing your counts on observations. you have in a corpus. You don't have global knowledge. And this is a crucial difference. Using observations means that you are only counting the things you see. You don't count everything in the language, and the language is quite rich and it's quite diverse. So the only thing you can do in order to make these observations as close as possible to the global knowledge or the real world is to collect so many of them. If you have taken the machine learning course or if you have taken the data engineering course, you probably remember hints at having the data set being larger, and larger data sets provide you with better knowledge just because they reflect reality much more accurately than smaller data sets. It relates to the concept of statistical significance if you have ever studied statistics and remember something related from them. Okay. So, in order to compute the probability of the word I here in that corpus, for example, given the start of a sentence, you only need to count the start of a sentence, which is going to be 3, and then you count how many times does the word I appear after a start of a sentence. So basically you want to count start of a sentence, then I, which is going to be 2 times, as you can see here. So basically the probability of having I after a start of a sentence is going to be 0.67. Does this reflect reality? Does this reflect the count of the word I at the beginning of every sentence that you can see in the language? Of course not. But here you are depending on a set of observations. This is essentially your data set. It's your corpus, whatever you want to do it. I urge you to do the computations yourselves. It's pretty straightforward. I doubt that anyone will make it wrong, but basically this is the rule you use. So here you can have more examples using corpora that is a bit larger than the toy example that we have seen earlier. There is the Berkeley Restaurant Project Sentences. It's basically almost 10,000 sentences with almost 1,500 unique words in them. So you can imagine the repetition of the words. These are example sentences that are extracted from the Berkeley Restaurant Sentences corpus. You can just play with this example in order to see how language models can be generated and how strong your generation of sentences is from this Berkeley Restaurant project alone, and how it can be generalized if possible at all. What I want to refer to is this. These are example counts, bigram counts. So we are basically thinking about a bigram model, bigram language model. This is an example of a count based on 8 words. Okay, so basically how you read this table is the probability of I given I, the probability of want given I, the probability of 2 given I. So how do we read the counts then? These are the counts. The number of times the word I appears after I is 5. The number of times the word want appears after I is 827 times. So the probability of I want, the count, sorry, of I want is equal to 827 times. Now, if you want to compute a probability out of this, you need to compute the count of I and then divide those in order to account for the probability of the word want after I. This is the count. Maybe here you have, I don't know, maybe you have 10,000 times, and then this is going to be the probability of the word want after I. So because essentially I can be followed by so many other words. So in order to make this clearer, you have I, and you have then so many words that could follow I. One of them is want. So I appears maybe 10,000 times in the corpus. Want appears after I 827 times. Of these, maybe I need, you can see here, I eat, for example, appears 9 times. I spend appears 2 times. Maybe I need appears 2,000 times. So basically, if you want to generate a sentence by generating a word after I, you need to compute the probability of each one of these appearing after I. The most frequent word appearing after I is going to be need, so probably you're going to say I need. Okay, what does this tell us about the counts? What does this example matrix tell us about the counts? It tells us basically that there are words that definitely appear more there are bigrams that definitely appear more frequently than others, as you can see here. And you have so many bigrams that do not have any probability at all, the bigrams that are associated with 0. So here, for example, you will never find the word to appearing after I. And you will never find the word want appearing after to want. You don't find it in the language. However, after to, you can find the word eat, to eat. And the word Chinese can follow the word eat so many times, 16 times out of all the times the word eat appears. But you may find, if you explore the entire data set, that the word English does not appear after the word eat at all. So here you have eat and you have Chinese, you have eat and you have English, and you have so many appearances of 0 in the matrix. What does that tell you about this specific corpus? It tells you about the impossibility of some sequences, want, for example, because of simple grammar. Grammar does not allow 2 verbs to appear after each other. Usually, people will never use 2 verbs sequentially. So some incidents are related to grammar. Even if you expand the data set, the probability will still be 0 for grammar. Okay, so if you have grammar impossibilities, the probabilities in this example will not change if you expand the data set. So they indeed reflect a fact of the world. They indeed reflect global knowledge. Here you have the word Chinese appearing a considerable number of times after the word eat, and you find that English does not appear after the word eat. This probably reflects cultural or societal preferences. People like to order Chinese food more than they order English food, and there is not really something that is called English food. Or it may reflect events that have not yet been seen in the world, in the corpus, sorry. So maybe we can say that there is some probability of the word food coming after the word spend, but we have not seen it yet because we are limiting ourselves to a corpus, and maybe if we extend the corpus to more sentences or more reviews, then we might find the 0 to have changed into a value. So the interpretation of the words or the counts here can either be due to grammar, that will not change even if you expand the corpus. It could relate to cultural preferences that probably will maintain the same rough probabilities even if you expand the corpus, or maybe they can change, we don't know. Or they can just reflect events that we have not seen yet in the corpus, but if you inspect another corpus, these counts could actually change. So here is an example of how you compute the probabilities of the previous matrix here. If the counts of the words are given to you, and you can inspect this corpus yourself in order to verify the counts and verify the probabilities. So, as we said, the knowledge that can be reflected, we can infer from the counts, is either social or cultural, or it can simply be grammatical. So we cannot make sure that the probabilities we compute here using this corpus are global probabilities. However, the focus is on the fact that these are the observations that we have, and we don't have anything else to aid us in computing better probabilities. So how do we approach this computation of these probabilities? Because again, as you can see here, if you want to compute the probability of I want English food or I want Chinese food, then you have to count the start of a sentence and the end of a sentence, and this is essentially the probability of I given start, probability of want given I, and so on. And there is a big problem here, which is this could be 0 or this could be 0, and you will end up with a 0 probability even if you have some information, or this could be very low, and this could also be very low, and hence you end up with a very low probability overall. If you choose to use more n-grams, then the probability will even get smaller and smaller, and you might end with an underflow. A very large number that is a fraction. How can we make things a little bit easier for us? You can actually use the log probability. So if you have probabilities here multiplied by each other, you can simply take the log and you end up computing the summation of the logs of the probabilities. It's faster and it prevents underflow. And usually this is what we will probably have to do instead of having to multiply the probabilities. This is what we can use to simplify things in exams, for example, or in computation, of course, on computer programs. Here are more data sets and more language models that you can find from the internet. There's the Cambridge Statistical Language Modeling Toolkit based on the Cambridge data set. And then here you have SRILM that also includes a data set combined with the language model that was generated from that data set. But also you have something great, which is the Google Ngram data set. It's a data set and an Ngram released all together. So you can actually access those through this link, and you will find that it can be read as this: serve as the incoming, so the count of this is 92 times. Serve as the incubator is counted as 99 times, and so on. You can check this on your own if you want to have more information about this. How do we proceed with evaluation of the model? We have seen how we can evaluate a ranked retrieval model by using the precision and recall at K. We have seen how we can evaluate a retrieval system without ranking by just using the precision, recall, and F1 measure. We have seen how we can evaluate a pause tagging by computing the accuracy of the tags that we have produced as opposed to the tags that exist already in a test set. So how can we evaluate a language model then? This is going to prove to be a little bit tricky. How do we interpret evaluation of a language model? Basically, what we want is, we want the sentence that will make the most sense. Apologies for the phone ringing. So back to the evaluation that we were talking about. The perfect measure of evaluating how a language model is to provide an assessment of the sentence that makes the most sense. It means something semantically approachable to the human beings. So how can we translate that into something that we can measure in a computer or in a programming, in a programmed code? Basically, what you want is you want to assign a higher probability to the frequently observed sentences, or the real sentences, or the sentences that make more sense. So the ungrammatical sentences, the sentences that do not have proper grammatical structure, should have very low probabilities or zero probabilities even. The sentences that you don't see a lot, however, have an interesting phenomena, which is they do appear, but you don't see them a lot. So their probability is going to be very low. But then we will fall into that trap that we have seen earlier, in which a rarely observed sentence can still be a meaningful sentence, much like what we have done in the TF-IDF computation. A rare word could lend more meaning or more relevance to a document, even if it does not appear anywhere else except in that document. However, we still have to use the observations that we have. There is no other way that we can do in order to assess whether a sentence really makes sense and really is a good sentence to be generated, other than what we have in the observations. So how do we proceed to use that? We have to the probabilities, which are the parameters of our model here, using a training set. Now, we have explained a training set and a testing set before, and we have seen how they can use in evaluation in post tagging. Same concept applies here. But again, remember that we are using an entire sentence and not just a simple word associated with a classification of the word. So what we'll do is we'll have a training set, and we have the data, and then we'll have a training set, and from the training set we will compute the probabilities, and then we will have a testing set, and we will use these probabilities to try and generate sentences and see if these sentences have a good match to the sentences in the testing set. So you will have sentences generated, and then ground truth sentences, and then you will see how good they match. You can see that this is a task that is simple enough. However, we will see that it has a major problem, and we will try to solve this major problem in a bit. But the essence of how this happens is this. You can take a word from the test set. Let's assume it's the start of a sentence. And then you compute the probability of all the words after a start of a sentence, and then you choose the word that appears the most. How do you how can you use the probabilities? It's basically the probabilities that you have computed using the training set. This is an evaluation that we can use in order to make more sound decisions. It's using extrinsic evaluation, meaning that you actually bring people in order to assess manually whether one sentence or two sentences generated actually make sense. Or you can just build two language tasks, and then try to generate sentences for these 2 language tasks, and then evaluate the accuracy of the generated sentences for these 2 language tasks. You can build a spelling corrector, you can build machine translation system, and then you use the language model in both, and then you assess whether the language model produces good translations matching the ground truth translations, or it produces syntactically correct and correctly spelled sentences, correctly spelled words. And then you try to see if your language model does perform well in both of these tasks. However, the problem with this is you can measure how many misspelled words and compare it to the correct words. You can measure how many words were translated correctly. The problem is this is going to be this is going to take a long time, because you have to run the task for a prolonged amount of time in order for you to be able to judge how good the language model will perform given so many cases. The problem is you don't have time. You just want to use your language model after evaluating the model in-house first. How do we proceed to do that? The only way that we have is using the training and the testing set separation. Okay, we do understand how we do that. But the problem with is the evaluation part. How do you compute the evaluation? Is it enough to use accuracy or precision or recall? Of course not. Why is that? Because you might end up with sentences that are slightly different than the sentences you have in the test set, but still they would be correct. So another measure that we can use is the perplexity measure. The perplexity measure is essentially a rough estimation of how understandable a sentence is. And it's intrinsic because it does not depend on external feedback from either humans or training tasks that we can have. Because basically you don't have language models just to have language models. You have them to use them in tasks. So it makes sense to use the tasks for evaluation. But as we said, this will prove to be a lengthy process. So what is perplexity then? Perplexity is a measure that was introduced in information theory. And I'm not sure if you have been introduced to information theory before, but I would strongly advise you to take a look at information theory topics because they prove to be very important, both in network and communication applications, and more importantly, in language. It would be unfortunate if you don't have an information theory course already taken. So perplexity is a measurement of how well a probability model predicts a test sample. That's a formal definition of perplexity. In informal words, perplexity is how confused you are when you read a sentence. So this confusion we can translate into a probability model, and then the probability model, if it's high, if the probability of the test sample is high, then we are much less confused. And if the probability is very low, then the sentence that we have is very confusing, and thus it has very high perplexity. So usually in language models, we use perplexity as a measure in order to evaluate how good a language model is. Again, we have to have a testing set and a training set, but the testing set has to not be part of the training set. They have to be mutually exclusive. However, they have to look almost the same. What does that mean? It means that same words, same structure, probably roughly same expressions. But it should not be identical to the training data set. and it has to be unseen before for the language model to work. So it should not be part of the data, the training set. It means that the language model has not seen this collection of sentences before, but the structure should be similar to what we have in the training set. Perplexity can be used just to provide a rough estimate of your language model. You cannot depend on it for prolonged use. So again, you will have to use an extrinsic evaluation metric. But here, at least you know a rough idea about the performance of your model, and you can compare two models together using perplexity just to decide which one to start with in the extrinsic evaluation. What is the intuition behind perplexity then? Basically, it's built on something that we call the Shannon game. Now, Claude Shannon is the one who invented the information theory scientific concepts. So in Shannon theories, you will find the clarity of a channel, the loss of data in a channel, and other important concepts. So what is the Shannon game then? It's basically this. Try to take a look at these sentences. I always order pizza with cheese and then you will have a collection of words that you are almost always going to use with varying probabilities, but they can be slightly different, not widely different. So you know what toppings you can use with pizza. It's just that there are so many of them, and then you will have to use one or two of them. So the probability of you saying mushrooms, for example, is going to be much higher than the probability of you saying fried rice. And it's going to be very higher than the probability of using and again. And, repeating and after and it's probably going to be a typo anyway. Now let's take a look at the second sentence. The 33rd president of the US was. There is only one answer for this, which is JFK. I'm not sure if you know of JFK, but this is the 33rd president of the United States. I saw a, on the other hand, is a sentence that has an unlimited number of words to use for completion. You can see how different these three sentences are. And therefore, basically what you want is a model that will assign a fairly high probability to the words that are expected in the sentence, a probability of 1 to JFK, and almost roughly equal probabilities for the things that someone can actually see. Now, if you use unigrams for this, you will not end up with very useful sentences. Why is that? Because the unigram here, for example, will give you a probability after was that could be anything. So they will guess anything. Every word that can be used for completion is going to be equally the same. It's going to have equally the same probability. So what we want is, we want a model that will assign a higher probability to the word that will actually occur. And this is the essence of how we can compute perplexity. So the best language model is the one that best predicts an unseen test set given the highest probability of a sentence that it has computed from the training set. So how can we measure perplexity? Perplexity is essentially the inverse probability of the test set, normalized by the number of words that appear in the test set. So here we have the probability of the test set. This is the probability as we know it. This is a sentence, so this is the probability of the sentence. But then we need to normalize it to the number of words that appear in order to maintain a proper distribution of the probability across the sentences. So this is the length of a sentence. You compute the probability of each sentence, and then you divide it by the length of a sentence to maintain the overall probability of the test set in order to measure performance over the entire test set. So basically this is 1 divided by the probability of the entire sentence taken to the square root, taken to the root of n, not the square root. And since we have already established that this probability is actually the multiplication of the conditional probabilities, if we follow the chain rule, and since we established that we can approximate using grams, and let's assume that we will use bigrams, so this is essentially how we can measure perplexity using either the chain rule over n grams or just using bigrams. So what we want to do is we want to minimize perplexity. Minimizing perplexity is going to be equal to maximizing probability given these equations. Maximizing probability means that we really generate the sentences that are indeed existing in the unseen test set. And therefore, we will have the minimum amount of confusion related to the test sentences in the test set. Okay, so let's take the scenario to just clarify the idea a little bit better. Suppose that you have a sentence that consists of random digits from 0 to 9. So we have random digits from 0 to 9, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now, the digits are random, meaning that every one of them can appear after the other with an equal probability. So that means each one of them has a probability of 1 divided by 10. Okay, so that means if you want to compute perplexity of this flow of random digits, then what you have is, if you generate 10 random digits, each one of them has a probability of 1 divided by 10. Then you multiply all of these together, and then you take the nth root of this probability, and you will end up with 10. A perplexity of 10 means that the branching factor is 10. What is the branching factor? It's basically this. When you have 0, how many other possibilities can we branch to? It's essentially 0, 1, 2, 3, 4, and so on, because the sentence is random. It's similar to this. This is what we can call the branching factor. And let's clear this. This is what we can call the branching factor. How many options do we have after the word and? And how much is the probability of each of them? If it's equal, then we have a random sentence. So here, in our case, since the digits are generated at random, then every digit in the sentence has after it another digit from all 10 with an equal probability. Therefore, the perplexity of this sentence consisting of random digits is going to be 10. So the next word could be any one out of the 10 possible words, and the probability is equal. As you can see, this is a very high value of perplexity contributing to a very low value of probability. So you can imagine that the inverse would be true. If you have a very high probability for a word, then you will probably have a very low perplexity produced. Again, perplexity, you can think of it as the amount of confusion that is produced by a sentence in your mind. So, a lower perplexity definitely interprets into a better model. And for that, you can expect that unigrams will have a certain level of perplexity, and as you increase the n-gram into bigrams, trigrams, and more, you will end up with less perplexity. Why is that? Because you are using more information and you are increasing the probability of a word appearing after another word. Here, probabilities are almost always roughly equal. Okay, but here, since you have bigrams, the probability of a word after a word gets a bit higher, and so on. So how do we generate text and then match it to the test set? You just start with a random bigram. Let's assume that it's a word given the start of a sentence according to its probability. And then let's assume that the bigram that we choose at random is I given the start of a sentence. Then starting from this point, you just choose a random bigram after that according to its probability. What is the probability of any word given I? Then you continue to do that until you reach an end of a sentence. So if the probabilities are properly attributed from the training set, you will end up with sentences that will make sense also in the testing set. Again, provided that what appears in the testing set does appear in the training set without the testing set having been seen by the language model before. Okay. A unigram, a bigram, a trigram, and a quadrigram models generating sentences from Shakespeare. And as you can see, as the models, as the grams increase in the n, you will end up with sentences that look almost as if they come from Shakespeare. The accuracy or the perplexity, related to Shakespeare will be very low because Shakespeare is one author. It has very consistent style, so you are very likely to generate sentences that do make sense as Shakespeare sentences. As you can see, it has almost 800,000 word tokens, and the distinct words are almost 30,000, sorry. And then you can actually do quite a decent prediction from the Shakespeare corpus because it's very small. However, if you use data sets such as the Wall Street Journal, it's going to be very challenging because it's a much larger data set. It covers a more diverse set of topics, and it's authored, because it's taking from the Wall Street Journal, it's authored by many people, and hence you will end up with more confusing sentences overall, even if you use higher engrams. So, again, we said that the test corpus should look like the training corpus for engrams to work for language modeling. But in real life, this does not happen. So if you take the Wall Street Journal as an example and divide it into a training set and a testing set, you can very well end with the testing set being authored by people who do not author anything in the training set, talking about topics or domains that do not appear in the training set, and so on. So here you will have a problem. So you need models that can generalize, not just abide by what appears in the training set. And if you recall from the matrix that we have discussed earlier, the matrix with a lot of zeros, these zeros could actually be values in other corpora or in other expansions of the data set itself. So you need to work around these zeros. So these zeros need to be smoothed so that you always guarantee that even if you have not seen the word before in the training set, it still stands a chance of being chosen in the generation for the testing set, even if it does not appear in the testing set. So in the training set, you can have deny the allegations, deny the reports, blah, blah, blah. But in the testing set, you can have denied the, but you have other two words like offer and loan that do not appear in the training set. But the problem is if you use our language model the same way that we have set them for the training set, so you will have a count of offer given denied the that is equal to 0. Henceforth, you will never be able to choose the word offer after denied the, and the sentence will never be generated. The probabilities of bigrams that have zeros mean that this bigram will never appear in the generated sentences, and therefore you will never be able to test it in the testing phase. And you will never be able to compute perplexity for a sentence in the testing set, because one of the words in this testing set does not appear in the generation, and therefore it will have a probability of 0, and then you will not be able to compute the perplexity in the first place because you cannot divide by 0. What can we do then? We have to smooth. What is smoothing? Smoothing is basically borrowing or stealing some of the probabilities of the words that have been already seen. So these are words seen in training. And these are words that are not unseen in training. But they actually appear. They actually appear in testing. So you have words that appear in training, and then you have words that do not appear in training but do appear in testing, in addition, of course, to these words which can appear in training and can appear in testing. What we will do is, since we have counts here for these words that are non-zero, and we have counts here for these words that in training are zero, but in testing are non-zero, then we will take some of the counts that we have here and lend them to these words that have a count of 0 in the training phase. So you have counts that look like this with a total of 7. You will take some of them and you will give them to another category, and then you still have a total of 7 counts. This is the amount of stealing that we will do, and we will distribute this amount equally for all the terms that do not appear in training but appear in testing. This is essentially the concept of smoothing. So, what do we do then? Since we are stealing the counts, it's essentially a technique of pretending that we have seen each word one more time than what we have already done. This is what will help us essentially achieve the smoothing. And this is what we call Laplace smoothing. It's a bad technique, but it's important that we understand it so that we can understand the better technique that can be introduced later. So again, the maximum likelihood estimate is the count of the 2 words divided by the count of the previous word. We will tweak this a little bit to make it the count of the 2 words plus 1. We have seen this word one more time, and divided by the count of the previous word. And in order to account for the fact that we have added 1 to each count, we will add the count of the vocabulary. Because since we have added 1 to each word in the vocabulary, we essentially add the size of the vocabulary here at the end. Now let's forget about this. This is a full rendering of the equations on this application. Why do we call it add 1 smoothing? It's Laplace smoothing, and it's also add 1 smoothing because here we add 1 more observation of each word. And hence these are total added observations of this word. Okay, so this is how add 1 smoothing would work. How do we try to make sense of it? We have seen that the maximum likelihood estimates are based only on the observations that we see. essentially what we have in the training set. Now, how we can translate the maximum likelihood estimation and try to map it to the real world, it's basically an interpretation of how frequent something appears in the real world, and we think that if we take a sample of the real world, then we will end up with roughly the same number of observations. So basically, if you observe the word bagel 400 times in a corpus of 1 million words, that means that every 1 million words you see, you will have the word bagel appear 400 times. So every additional 1 million words that you see, you will have the bagel word appear 400 times. We think that this is the best estimate that we can have. It might be bad for some of the corpora, but it's the best thing that we have given the corpus that we already can learn from. So here we are tweaking this maximum likelihood a little bit, because here we don't observe the word one extra time, and of course we don't have an extra number of vocabulary size added to the words in the corpus. But we are just trying to play with the maximum likelihood and make it and tweak it a little bit for the advantage of trying to address the unseen words, something that the maximum likelihood will never catch. So what we will do now is we will add 1 to each count. As we have seen in this equation here, we add 1 to each count. This is what we have done. And you can just go back to the slide in which we had the matrix, the original matrix, in order to compare that we had zeros that are now ones, and we had 827 that is now 828. Now we have increased the size of the bigrams that we see by V. So we need to do some tweaks on the probabilities and the actual counts in order to maintain the rough estimation of the probability even with the increase in the counts. So how do we go about doing that? We compute the probability now based on the add 1 smoothing, the one that we see here. So since we have added a number of ones that is equal to the vocabulary size, you can compute the vocabulary size from the original vocabulary size by the summation of the word counts that you can find in one of the previous slides. So it's the summation of the word counts. Now, each count that we have here has already been added, has already been incremented by 1. So here you will have 828, because it's 827 plus 1. And then you divide it by the count of the word, which is the word. Let's take, for example, this 828 is the want given I. Okay, so you take the count of the word I. Take it from a previous slide that has the matrix with the counts. But you need to add a vocabulary of size V to that. You end up with these probabilities. The thing that you will have to do next is you need to restore the counts after the smoothing. So here is the probability of the bigram given the previous word. Here is the probability of the bigram plus 1 given the previous word count plus the vocabulary. These two probabilities have to be the same. So basically what you need to do is that you need to change these counts. How would you do that? You will just reverse this equation. This is something that is equal to this, so you just need to count this because this is going to be the same. This is the total. And then you will end up with adjusted counts. So as you can see here, the counts have changed a lot. Here in the next slide, I guess, we have the counts compared. Here is the original. And here are the counts after smoothing. You can see that the counts have been discounted, stolen, or maybe the more politically correct term, borrowed. You can see that all of the counts that were 0 before now have very different probabilities. Some of them are very small, some of them are quite large. Depends on the frequency of the preceding word, of course. I'm guessing that you can infer that these changes will depend on the preceding word, of course. But you can also observe that the counts that were originally high are now discounted to lower values, sometimes cut down by 2/3 even. You can see that the numbers here are quite different. So that essentially means if you take the total of this and the total of this, the sums will be the same. Because of that, the probabilities are also the same. So this means that basically what we have used is incrementing each bigram by 1, then dividing by the count of the preceding word plus the entire number of ones that we have added. And then this is now the new probability, but we need it to be equal to these original counts, so we will need to recompute the counts. And how you do recompute the counts? By just doing simple mathematical substitutions. This is basically what Laplace smoothing does. This is the technique it uses in order to borrow some of the counts here and lend them to the counts that were originally 0. The problem with add-1 smoothing is it's hard-coded. It's almost hard-coded. Usually, add-1 smoothing is not used for language models because you force the addition of 1. But it can be used for other tasks that are NLP related, such as text classification, or if you don't have a large number of zeros in your corpus, then language models that depend on Laplace 1 smoothing will actually work fine. But it will not work well if zeros are many. Because here you're essentially generating a completely different data set than the one that you should be working with. So how do we introduce improvements to this add-1 smoothing? I will add an auxiliary or an additional VOD that explains the improvements that we can have on the add-1 Laplace smoothing. Until then, I hope that you keep safe and sound, and I will see you next week, hopefully, for our final lecture before the midterms. Until then, please keep safe and sound, and I'll see you in good health. Goodbye.